Let us now expand some ideas about replication. So in the following two tables, what we have are extreme cases of experimental situations we should avoid. Okay, so let's see what are they. So in both cases, in both experiments, we have 8 different treatments. And we know that because the number of degrees of freedom for the treatments are 7. So we have 8 different treatments. And then in this example, we have only 16 experimental units, and in this one we have 500. In both experiments, the treatments and the errors, they both explain half of the total sum of squares. So this is 16, 16, this is 500, 500. And then if we compute what is the mean squares of each one of the factors that we have that the mean squares of the treatment is 1 here, that is 16 divided by 7, and this is 2, that is 16 divided by 8, and we compute the same here. So in this case, when we compute the signal to noise ratio between the treatments and errors, that is this F statistic, in this case we have very little effect, while in this one we have an extremely high effect. And the reason is that here we are having very little power, statistical power. We have only 8 degrees of freedom for the errors when we have 7 degrees of freedom for the treatments. So I don't mean that the treatments will be all effective or not. We don't know yet. So maybe all the treatments are the same. But what we are sure is that having the same number of degrees of freedom is really a danger, because we will not have enough power to detect changes in the treatments, and that is given by this F being very small. And this is the opposite situation. Now the F is extremely high, and the reason is that the errors have been divided by a lot of degrees of freedom, and that gives you a lot of so you made way too many samples for this experiment. So these two situations, having too little power or too much power, is bad, especially if you are doing experiments with animals, in which it is unethical to do experiment with in either situation. So if you have too many animals, it is unethical because you don't need so many to prove what you want to prove. And if you have too few, because it doesn't matter what you do, that your treatments will not be your analysis will not be able to show that the treatments are effective or not. So the experiment is inconclusive, and you have done the experiment for nothing. So you have to avoid both situations, and in general what is recommended is that the number of errors is somewhere between 15 and 20, or 10 and 15. 10 and 15 depends on how many degrees of freedom you have you need for the treatment, but something in that range around 20 is relatively recommended to have enough power. But still, what is absolutely recommended is that you design your experiment and you do a power analysis and you compute the sample size that you need to be able to detect a particular given effect size. So the replicates are how many samples you have in the experiment, will help to gain degrees of freedom and for the errors, and then this will help you to say whether the treatments are effective or not. And if you have a completely randomized design, so this is the equation that models your measurements. So you have different treatments that we will refer to with I, and then you have the person J within the treatment I, and that will have a residual. And then at some point, let's say that you reject the ANOVA hypothesis, so you will make a postdoc analysis to check which one of the treatments are different. So you will compute differences between the effect of treatment I with the effect of treatment I prime. And let us say that we have Ni and Ni prime replicates in each one of the groups. So this group has Ni, this one has Ni prime. So the variance of these comparisons is this one. So it is the variance of the noise divided by this sum, or multiplied by this sum. And we see that replicates not only help to reject the whole idea of all the there is no difference between treatments, that is the ANOVA test, but later when you are doing the postdoc analysis, they will also help you to determine which one of the treatments is really different from the others. Let us study a few other ideas about this. So giving a drug to two different people is a true replicate, but giving a drug twice to the same person is not. And the reason is that the same person, the two measurements coming from these two observations, they're coming from the same person, so they are not independent. So replicates are truly independent. A macroarray technical replicate is not a true replicate, but it is a technical replicate, but biological replicates are. So if you measure multiple macroarrays on different individuals, then that is a biological replicate. In an animal feeding experiment, pigs within the same litter are not the replicates. The experimental unit is the litter, and a true replicate is another litter. Automatic measurements on the same subject do not provide replicates, but time measures. So this is this repeated measures design. Now there are devices that give you measure every 5 minutes of the individual, but all those numbers are not individual replicates, so you don't have a very large N. Here it is an interesting example about the effect of dealing with non-replicates as replicates. So you have non-replicate data, but you think that they are true biological replicates. So let's say that you want to determine the effect of 3 different teaching styles on student learning. And to do so, you take 9 classes. These classes are randomly assigned to each one of the 3 teaching styles, and then you do a final assessment. And depending on the time of the assessment along the day, there is some pattern, because students in the afternoon are more tired, and this has an effect on the final assessment. Okay, so you make a test, and you have the 3 different styles of teaching, and then you have the classes A, B, C, D, E, F, and so on. And then you have these are the scores for first treatment, second treatment, and third treatment. So you compute the ANOVA table, and the ANOVA table, well, this is the variance, this is the sum of squares of the treatments, the sum of squares of the errors, the number of degrees of freedom, and the mean squares, and then the F both show, okay, there is not really an effect between the different teaching styles. Okay, now instead of making just one test, you do 4 tests in 4 consecutive days at the same time, to avoid the diurnal pattern. And then these are the results for each one of the classes. And now you compute again the sum of squares, and what you see is that now the F has gone from 0.5 to 3.4. So something that was not significant before now is significant. But there is a problem. All these measurements, they are not independent. So you are measuring 4 times the same class. So you are measuring 4 times the same value. So the number of degrees of freedom is not truly. So here we have nine classes measured 4 times. So you don't have 35 degrees of freedom. You have many less because the samples are not independent. So if you really want to have 35 degrees of freedom, what you have to do is to repeat this experiment 4 times with 9 times 4, so 36 different classes, not just the same 9 classes measured 4 times. Okay, so now let's say that you have only one class to do the test. So whenever you want to have an exam, you have to move the class to this room so that they can take the exam, and then you distribute the different 9 classes along the 4 days and then the teaching hours. So the first day uh, class A will do the exam at 8, then class B at 9. So you see that the sequences are pretty random, which is good. The problem is now that when you measure the variability and the sum of squares expressed by each one, now it becomes not significant again. And the problem was this. So there are two problems here. First problem is that we are measuring the same class 4 times, which we already know that that shouldn't be done. The second problem is that now, because we are not doing the exam at the same time, there is much larger variability. So these errors now, they're much bigger. They're much bigger because of this variability over time. So now something that was significant is not significant. So still, we shouldn't do measure the 4 times the same class. But if we want to take time into account, what you have to do is to introduce it in the equation of the analysis. So a time would be now a block. So you should have the contribution of the block here. So you have the treatments plus the contribution of the block plus data sequence. Now this block variable will explain a big part of this increase in the observation of the measurements. So this is what we should have done. So we should have included time as a block. Let us consider a following example. So we are measuring the effectiveness of 2 fungicides, and the fungicide may be applied on the upper or the lower side of the young or old leaves. So we have a factor that is upper or lower side, we have another factor that is young or old leaves, and we have another factor that is the fungicide. So in total we have 8 possible combinations. And the experimenter measures the amount of fungi in a small disc of the leaf, and the treatment is replicated 10 times per combination. So you have an F of 500. So an F of 500 is a little overkill. So we are in the same situation as we were in here, where we have way too many samples for what we want to detect. So we should have design our experiment in such a way that we measure what is the variability, and in terms of this variability, we design how many samples do I need to be able to detect this change, this amount, this kind of changes. So probably we wouldn't need 10 replicates, technical replicates. Okay, and what is well, we don't know yet if those are technical replicates or not. Okay, so what is the when you dig into how this particular experiment was carried out, we see that fungicide 1 was applied to tree 1 and fungicide 2 was applied to tree 2. So we already see that we have a confounding effect here. So we don't know if the difference in fungi is caused by the fungicide or is caused by the tree. So the tree and the fungicide have been confounded. So we should have used the tree as a block, and then each tree should have seen both fungicides. And the 8 treatments were applied to 8 leaves. Okay, so we have only information from 8 leaves, and the replicates were obtained by cutting 10 discs from the same leaf. So now these 10 discs, we know that they are technical replicates, not biological replicates, which are fine. So you can measure the same object 10 times, but then what you have to do is to compute the average of all those measurements and combine and assign that average to the measurement of the leaf, and the leaf will be the experimental unit. So the 10 replicates are not true replicates, which are biological replicates, but they are measuring essentially 10 times the same thing. Let us consider these two different proposals for measuring the effect of some hormone on the growth of animals. So you will give some hormones to different animals, and you will measure how they grow, and you will see the difference in their weight after 6 months. So a possible setup is that all animals in the same pen, they receive the same treatment, or the same here, or there is an alternative that is 2 animals will receive A in the same pen and 2 animals B in the same again. So is there any design that is preferable over the other? So here the treatment and the pen are confounded. So if we see differences, we don't know if it is because of the treatment or because of the pen effects. So maybe there are some dynamics here that explain that are different from the dynamics here. So the social interaction, and the differences are not because of the hormone, but because of these social differences. That could be. So this design has problems, so we would prefer this one in which that doesn't happen. But there is a catch here. So the catch, and the catch is that, let's say that, yeah, so for instance, assuming that we count for the pen effect, so to account for the pen effect we need to replicate, to have multiple pens of this kind, multiple pens of this kind, and then we can measure the pen effect. Okay, but anyway, let's say that A makes the pigs to be more aggressive and B more docile. So this kind of design here, it would have a problem, because the hormone doesn't make the animal to grow more because better metabolism or more slower metabolism or whatever, but because they are more aggressive and then they have more access to food. So if we use this design, all the animals in the same pen, they are equally aggressive or equally docile, and then we wouldn't see any difference between the hormones. So both, so the problem here is that there is an interaction. There is an interaction between factor levels and the pen, and the design. This design is not able to get it. So the main message here is that there is no optimal experiment design. So statistics cannot tell you what will happen, what is the effect of the hormones, why you see these differences. This is up to the experimenter to know, and statistics can tell you what you will be able to detect if this is the situation. So if there are interactions between hormones and the blocks, then with this design you will not be able to detect them. If you want to have into account the pain effect, you have to replicate this design multiple times. So statistics is a good tool to understand and analyze data, but it is not a substitute of your domain knowledge. Okay, so we have said that the experimental unit is the minimal experimental material in which you can change the treatment. So let's say that you are interested in the growth of plants at 3 different temperature levels. And then you have a greenhouse, and these greenhouses have different rooms, and you can change the temperature of the whole room. So for instance, let's say that you have 6 greenhouse sections and you have 3 treatments, so each one of the temperature levels will have a couple of greenhouse sections, so a couple of rooms. So the experimental unit is the greenhouse section, so it is the room, because that is where you can change the temperature. But and having 2 replicates is not too much. So can we use the individual plants as the experimental unit? Technically no, but we all realize that otherwise it would become very difficult to analyze this effect. So we can use the plant as the experimental unit if we may assume that the greenhouse sections do not affect the plant growth, so other than the temperature. So it is not that one of the greenhouse sections is facing north and then it receives less light, and the other one is facing south and then it receives more light. So if that is not the case, that is one of the conditions. The variation between plants are essentially due to plant variation and not to anything else, like the north-south example that we have given, or there is no competitive variation, or having more humidity or less humidity. There is no competitive variation, so like in the pig case where the hormones make them more aggressive between the plants within a section, and this competitive variation has been induced by the treatment. So if all these conditions hold, then you can use the plant as the experimental unit and not the greenhouse section. Okay, so this would be all for replications, and in the next block, in the next section, we will have blocking.